Welcome to CITP seminar. It's our great pleasure to host Professor Varshney, the professor at the University of Illinois, Urbana-Champaign. He did his PhD at MIT in information theory, trained directly with the roots of Claude Shannon and as a theoretician. But the signature event of Love is creativity. I think if I want one word to describe Love, and his work is creativity. And he's used his creativity across the span of theory to policy to computation to algorithms, a remarkably diverse range of creative activities. He's also looked for computational roots of creativity. So he's just back from a stint at the White House and as a White House fellow at the National Security Council, where he was helping draft the AI executive order by the president, part of the India-US wireless communication collaborations, US 6G policy.
Yeah, kind of a joint statement that we developed. That's right.
And he was definitely in charge of requests for proposals for a digital dollar, CBDC. I know because I submitted some ideas there. Welcome, Love. It's a great pleasure. CITP is the perfect place to host your diverse interests. We're looking forward to it.
Yeah, no, thanks, Pramod. And yeah, it's great to be here in Princeton. I'll jump right in. So this kind of this is the first time I'm actually talking, or I have never written about this topic. So you guys are kind of my guinea pigs. And as Pramod mentioned, I'm an information theorist by training, and then I've worked in AI for some years. So been exploring some other emerging technologies in biology and quantum recently as well. And when I was serving at the White House, I was given that kind of crash course in policymaking. And it kind of struck me that engineering theory ideas might actually be relevant to policymaking. They seem like they might be quite abstract and maybe disconnected, but perhaps quite connected. And so what I want to try to argue is that there are kind of a variety of ways in which engineering theory might be quite useful for emerging tech policy. And in a way, this talk is a response to a question I got about 15 years ago when I was interviewing for faculty positions. So I was interviewing in an electrical engineering department, and one person in my talk asked me, like, why is information theory useful at all? Right? I mean, you probably shouldn't, ask a faculty candidate to defend their whole subfield, but I mean, in any case. And I answered in some ways, but I've been thinking about that question for a long time now. Is like, what is the use of theory in practice? And so I want to kind of try to argue through that. Yeah. Right. So one of the things that we've been thinking a lot about is that emerging tech, including AI, but others as well, are proliferating through various industrial and societal sectors. Just to give like some examples, and I'm going to use some of examples from my own work just because I'm idiosyncratic. And also I'm going to use my own work as a bit of a straw man. I didn't want to use other people's work for that. Right. So we've been using AI for engineering design, for operating systems, for maintenance. So, you can design new proteins, you can design new formulations of concrete, which have half the embodied carbon as traditional concrete, but are just as strong. And this is actually kind of a neat project. This was actually deployed in a new data center that Meta was building in Northern Illinois, kind of $1 billion plus project, and they used our concrete. So it was kind of fun to go and walk around there. Or like in culinary, it's fun to eat your own food in some sense, or optimizing wastewater treatment plants. Right, so these are like kind of examples of where emerging tech is really proliferating across societal sectors and industrial sectors. And as you might have seen on my first slide, I'm also working with a startup called Concrete, and I'm on sabbatical this academic year, so I'm spending a little more time at the company, and then also spending a little bit of time at Northwestern in their business school. And so like another example is actually using AI to help design or compose new music, very much capturing the hip hop ethos of taking pieces of music and then recombining it into new compositions. Right. So the fact that AI is and other emerging tech are kind of diffusing so broadly raises the question: should we be having strong policy? And there has been a lot of effort in that direction. And kind of yeah, when I was preparing for this talk, I had a bit of an email exchange with Alondra Nelson, and she was kind of encouraging me to go ahead and give this talk, even though I've not presented it before, and also kind of trying to like make sure that I have kind of socio-technical policy making in my head, which I think many of us do, right? We've been thinking about this for several years. We've been working to ensure the social part of socio-technical policymaking is part of how we approach things. I think it's not really possible to understand socio-technical perspectives without the technical either. And so that's kind of the genesis of the argument I'm making here, is that I think we all are starting to make sure that we have social aspects of socio-technical in how we approach policy, but maybe we might actually be losing some of the technical, in the sense that public policy is more than just applied political economy. Of course, there are questions of market failures like information asymmetries, externalities, collective action problems, and so on that we want to address through policy. But there are other elements to public policy as well that require some reasonable understanding of the technology itself. There are limits to what technology can do. And I think keeping that in mind actually helps with crafting good policy. And yeah, I should say, as Pramod mentioned, my training is in engineering theory, so I feel slightly inadequate speaking here. I did take a class in grad school on science policy, and my professor there was used to just really hammer home the political economy points. But I think one can go beyond that a little bit. Right. So certainly we want to avoid abstraction traps of the type that Selbstedal described. So when we kind of make abstractions, we want to make sure that we do include appropriate social criterion. We consider context. We make sure that when we formalize in the ways that engineering theorists do, that we capture the appropriate aspects of what we care about. And broadly speaking, I mean, engineering theory does have to start with creating closed deductive systems. I mean, one has to define kind of a closed space, and then one proves theorems in those closed spaces. And then one tries to take the insights from that and bring it back out. And further things like the ripple effect and solutionism traps. Right, so certainly we want to keep these abstraction traps in our heads as we proceed in policymaking. But another trap that I want to avoid is a different one, which is that maybe we abstract away the technology too much as well. This is a quote from a textbook by Dorfman, Samuelson, and Solo from 1958, but I think it's still as true today as it was whenever that was 60 years ago. Right? Technologists regard the production function as an economist concept. And as a matter of history, nearly all the production functions that have actually been derived are the works of economists rather than of engineers. Which is to say, often if an economist is thinking about technology, they just think of it as a simple factor of production. It, in some sense, rebalances labor and capital, and that's all they say, perhaps. But there's more, and even within this kind of framing of production functions, there's details of the engineering that matter. Another thing that I feel is that when thinking about policymaking, people often have the physical engineering artifacts in mind. So they might have a big and specific physical infrastructure in mind, like this is perhaps the largest engineering project in history when the Chicago River was reversed, and it required these reservoirs that are this is, I think, the size of 14 football stadiums, and this is only one of the reservoirs. Right. So, and this is something I actually worked on a little bit myself. So, so this is kind of the big physical infrastructure is what is an example of an engineering system that people have in mind. Or they have small and specific physical devices in mind. So they might have particular computer chips, and the specific artifacts are what they're thinking about when they're developing policy. Or they might even have kind of a somewhat naive view of engineering that's kind of been propagated by media. So if you ever read this children's book, Rosie Revere, Engineer, she basically kind of hacks together random junk to make things. Or if you watch this movie from Bollywood called Three Idiots, again, I mean, the core premise is that you can hack together pieces of essentially junk to create engineering artifacts. Right? And kind of this approach to engineering theory where you want to have fundamental limits, principal designs, the ability to predict and characterize is largely lost. Okay? And when one has kind of this very physical and very specific notion of engineering or even this kind of hacking culture in mind, I think it kind of pushes one away from drawing on the appropriate techniques from engineering theory. So let me describe a few examples of kind of engineering-ish, theory-ish approaches, but that are very specific. And then I'll try to argue that maybe one can actually use more abstract approaches as well. Right, so this is a paper that we did on food security. So we looked at the flow of food across the country. Where does food start? Where does it go? And so on. And we figured out where the choke points are. These are the hubs that connect production, processing, and consumption of food, and whose disruption would most impact kind of the agri-food supply chain. Right? So the figure shows kind of edges originating from the starting point. So this is at the BAP level, and this is at the county level. So you notice, for example, Long Beach, the port of Long Beach is a big choke point. Right? And so this is a very specific kind of analysis. It tells you the methodology is somewhat general, but it's very specific. It tells you if I want to invest in securing the food supply, I should really help strengthen the port of Long Beach or Chicago or wherever it is. Okay. So this is arguably a mathematical approach. It uses network science, but it's very specific. Another example is when I worked in the city of Syracuse, which is my hometown. So we developed an algorithm to prioritize which houses that are abandoned should the city take liens on and try to flip to occupancy to improve urban sprawl, to improve kind of various factors in quality of life. Right. And so again, various general methodologies in some sense, right? We built a predictive algorithm that took a bunch of features, made predictions, prioritized the list of houses. And this was actually used quite a bit in Syracuse. Just in the first year, it led to, I think, $5 million of impact. And the HUD kind of used it as an example to spread around the country. But again, it's using kind of engineering techniques, but for a very specific setting, right? I mean, this block diagram is fairly complicated, right? Or you can think about agricultural policy. So there's growing interest in AI-driven climate change impact prediction. So where I come from in East Central Illinois, we grow a lot of corn. And so what one can do is ask, so if there's scenarios in the next 50 to 100 years of climate change, how will that impact agricultural productivity? And again, it suggests a variety of policy levers one can pull in agriculture. And one can, again, see kind of this Central Illinois is one of the highest yield parts of the world for corn. But again, it's a fairly complicated, specific characterization of the phenomenology of agriculture, and then doing engineering on top of it. So these are kind of three examples I wanted to show that this is not the kind of engineering theory-based policymaking I mean. I mean, this is compelling. I mean, I worked on it myself, but what we want to think about is something else. Right? So engineering systems theory rather than models of specific phenomena. And so engineering systems theories respect the constraints of physical laws, but they're theories of what can be. of the myriad possibilities of what's possible and impossible. And to do that, they abstract from most physical details to allow kind of the maximum freedom for engineers to create useful things. Right? They're abstract, they're mathematical, they create these closed deductive systems, and they get rid of as many details as they can while still being insightful. Does that make sense, the distinction I'm making between kind of physical engineering and these kind of more abstract engineering systems theories? Okay. Right, so these include fields like information theory, control theory, statistical learning theory, etc. Okay, so just to give some examples of kind of famous results in engineering systems theory. Right, so if one thinks about thermodynamics, Carnot in his, when was it, 1824 book, I think, established the fundamental limits on the efficiency of engines. Right, so you can't make an engine more efficient than the Carnot engine. And further, that was kind of inspirational for the diesel engine, that the insight was that if you raise the temperature, that makes the engines more efficient. Another key example is Shannon established the fundamental limits of reliable communication in the presence of noise. So he was concerned with communication of any kind. Anything that fits into this block diagram is communication. And asking what's the best one can do. More recently, Karaman and Frisoli established a fundamental speed limit of flight in forests without crashing. Sertaj Karaman was my roommate in grad school, actually, so we used to talk about these ideas quite a bit. And so he worked out, so if you have like a drone or a bird or something that's flying and it has only a limited ability to turn, it can only go so fast without crashing. And in fact, if you go just above that speed limit, you'll crash infinitely often. If you go just below that speed limit, you can fly forever without crashing. So there's a fundamental limit, there's a threshold phenomenon. And it's the same in communications. If you try to communicate at rates greater than the channel capacity, your error probability will go to 1. If you communicate at rates below capacity, you can achieve arbitrarily small error probability. Right? And so that's often the hallmark of these engineering theories, that there's a very precise threshold. So below things, you can do it well. Above things, it's impossible. And that's what I meant by demarcating between possible and impossible. And I think I already mentioned this, but let me emphasize the point that to develop these engineering theories, you need to have some sort of mathematical abstraction. To quote Bruno Latour, the sociologist of science, he says that Carnot's know-how is not about building a machine, but rather a diagram. This diagram is drawn in such a way that it allows one to move from one engine to any other, and indeed to non-existent engines simply drawn on paper. Right? Real three-dimensional steam engines are interesting but localized and cumbersome. Right? They're physical, they're specific. But if you can diagram it, I mean, that's where theories come. Or Shannon himself said that frequently messages have meaning, that is, they refer to or are correlated according to some system with certain physical or conceptual entities. And then he casts out that property. He says these semantic aspects of communication are irrelevant to the engineering problem. Right? So, so Shannon says that anything that's in the block diagram is communication. Everything that's external to it is not. So you can prove mathematical theorems within the diagram, but not that side. Okay. And one can do other things along these lines. So one can develop kind of limits on reliable computing with noisy hardware. So this is something I did with Naveen Verma here at Princeton and my colleague Naresh Shanmugh and others. Or one can ask, are there limits to creativity, like Pramod was mentioning? Right, so if you've been building a lot of these generative and creative systems, it's very natural to ask, like, am I doing a good job or not? Right? Maybe you are, I don't know. So it's nice to have this fundamental theory, or kind of limits of deepfake detection. Right. So for any of these kinds of problems, you can ask, what's the best I could do, or what's the best any engineer could do, no matter how clever they are, like how much effort they put in. And that's what comes out of these kinds of theories. Okay, so so that's good. So is it actually useful to have these limits within engineering? Right. So William Pierce claimed that what every engineer needs is a good set of limit theorems. and why. I just build it like Rosie Revere. So why do I need limit theorems? So there's at least 4 reasons I would say that you would want these kinds of limit theorems. First is actually on the fundamental part of fundamental limits. So first we want to establish which resources and performance criteria are fundamental and which are largely unimportant. So if we're looking at communications, it's things like power and bandwidth are perhaps important, maybe circuit complexity. And in terms of performance criteria, it might be things like information rate or error probability. And there might be other things that are largely unimportant. Like volume is, for communication systems, it's useful when you're building cell phones, but maybe not when you're building transatlantic cables. Okay? So maybe volume is not so important. Secondly, you might want to demarcate what is possible from what is impossible, right? And it's useful to know what's impossible. So if you're already close to that boundary, maybe you can stop. That's one of the key difficulties that a lot of engineers face, is that they always want to keep improving, right? They want to keep working hard. But once you get to that fundamental limit, no matter how hard you work, you'll never pass the limit. So it's good to know what's possible and what's impossible. But also, that boundary actually provides design insights. You can get kind of principles or architectures for optimal designs that come from that characterization of the boundary. To take the example of information theory, there's something called the capacity achieving input distribution. And that actually tells you, broadly speaking, how you should design error correcting codes. Okay? Or this theory of creativity that I developed. That boundary, in some sense, tells you how to build a generative AI algorithm. Okay? Not specifically, I mean, it's not fully constructive, but it roughly gives you a sense for it. Third, it allows you to define fundamental benchmarks. In a lot of fields, there's this idea that if I'm doing 10x better than someone else or 100x better than someone else, that I've done a lot better. And this relative performance, I mean, it's a good way to think, but absolute scales are even more insightful, right? So now we know exactly what the best possible thing is and how close am I to that. Then fourth, it actually states ideals for pushing people to build technologies that approach or achieve those absolute limits. Okay. Everyone likes that challenge of doing the best that's possible. Okay, so engineering theory maybe is useful for engineering. Hopefully you agree with me. I mean, my whole career is based on that premise. But is it at all useful outside of engineering? Right. So for to take an example, theoretical neuroscience, yeah, it does seem to help. So you can compute kind of the limits on how much people can remember or how people perceive or how quickly organisms can act. And again, kind of engineering theory optimizations allow you to predict a lot of properties about what's experimentally observed. Okay. So there's a bunch of examples where engineering theory is useful outside of engineering. And the question we want to ask today is it useful for policymaking? So does everyone know who this guy is? This is the differential analyzer at MIT. The big analog computer that was developed in the 1940s before the war.
Vannevar Bush.
Yes, this is Vannevar Bush. That's right. So many of you know him as kind of the architect of the post-war scientific system in the US. But what's interesting is this guy. So any guesses on who this guy is, his assistant? Who like just barely made the photo. Yeah, this is actually Claude Shannon. He was an assistant to Vannevar Bush. Yep, and yeah, luckily got in the publicity photo. So what Bush had put forth kind of as a philosophy of science policy was that there's an endless frontier, that science and engineering can advance the human condition quite considerably, and there's no particular limit to it. On the other hand, Shannon is kind of one of the prime architects of engineering theory, right? He established these fundamental limits. And it's kind of funny that they worked together. And I think sometimes we fall into this trap that technology is actually an endless frontier. I mean, that there's no limits at all. But there are. I mean, there are limits to what can be done. And so that's why thinking about theoretical limits is helpful in policymaking. Right. So let me give you an example. Right. So there's been a lot of interest in planting trees. It seems like a good idea. I mean, they absorb carbon, they rejuvenate degraded landscapes, they can often support local livelihoods. But can you just like plant trees everywhere? That's often been a belief that that you can literally just plant 1 trillion trees around the world. And there's been these massive tree planting policies under kind of national, international, and donor funded programs. And in fact, this is very much a colonial fascination. So colonial forestry kind of asserted that, you know, over the last several centuries, you can plant trees as a solution to a variety of ills, whether it's drought or temperatures or so on. But a lot of recent studies have shown that there's actually a lot of negative impacts to planting trees in places where they don't grow. So they might grow for 6 years, but then they'll all die. I mean, that's bad ecologically, and it's also bad for people's livelihoods. There are actually carrying capacity like limits. There are fundamental limits to how many trees you can plant in a given area. And so what we did was we computed for the North Indian state of Himachal Pradesh that the maximum tree cover that you can achieve is about 32%. Based on a variety of biophysical and sociological constraints, which is much less than the stated Indian goal of 66% of the total area of the Himalayan states being forested. Right, and then that 66% number actually comes from the British era, and it hasn't changed since then. It was developed with very limited understanding of forest ecology. Right, so I mean, the number of trees you can, like, even if you planted trees everywhere where they would sustainably grow, you would only have half the target. Right? And so the point is that once you start thinking about limits, it helps you think about what are appropriate policies or not. And in this case, it actually helps you decolonize the policy making. Okay, so so that was kind of a introduction to what engineering theory is and why it might be relevant for policymaking. Now I'm going to dig into several vignettes to try to make the case a little bit more strongly. So I'll talk about 3 ideas in informing policymaking, and then I'll talk about engineering theory as a policy lever itself, which seems kind of silly. How can a theory be a lever of policy itself? But what I'll try to say is that there's these mechanisms of performativity that the world could actually become more like the theory that was developed to describe it. And then secondly, that you might be able to counter some called philosophies of computational positivism, which I'll get into. Okay, so let's talk a little bit about AI, large language models in particular. So some years ago, I worked on this project where we built a billion parameter plus language model back in 2019. If you gave a prompt like this one that, you know, like a made up CNN URL, it would generate some text. No, it was reasonably fluent. It's factually reasonable. Back in 2007, the president was George W. Bush, the prime minister was Tony Blair, there was a war in Iraq, etc. Right? So, so it's quite reasonable. And in November of 2022, we saw ChatGPT come out, which seems to have greater capabilities than the control model that I just showed you. But like, how do we characterize that? And there's a lot of interest in policymaking around the world, in the US especially, of kind of fears around these large language models. So is there a way to regulate these things? So there was a kind of a long process at the White House and in federal government about thinking about AI regulation. There was an AI blueprint for an AI Bill of Rights that the Office of Science and Technology Policy developed, which set out a variety of principles. NIST developed the AI risk management framework, which tried to be a little bit more specific about what that means. There were these voluntary commitments from leading AI companies to manage risks posed by AI, which was in the summer of 2023. And there was this executive order on the safe, secure, and trustworthy development and use of AI. This came out in October of 2023. So, a lot of kind of a progression, ideas, then voluntary commitments, then executive order. Further, the vice president made kind of commitments on US initiatives at international level. We did some stuff on US-Europe relations to bring democratic countries together to collaborate on AI, et cetera. Right, so, a lot of efforts around regulation of AI, right? I mean, I just showed you a lot of slides, but that was the takeaway, right? A lot of things happening. More recently, so in July of this year, it was the 270-day mark since the executive order. There were a lot of deadlines for accomplishing things by then. And one of the things was that the Department of Commerce released an interim rule on reporting for large AI models. So it required quarterly reports on training activities, cybersecurity measures, ownership, red team testing, et cetera. And the Bureau of Industry and Security estimated that it would take about 5,000 hours per year for doing this kind of reporting, right? So not a huge burden. That's about 9 weeks of someone's effort. And this was really meant for kind of roughly the 15 companies that are building these largest models. But how does one say what's a large AI model? And so this is the approach that Commerce took based on the executive order. So they used compute thresholds. So they said anything with more than 10 to the 26 flops or integer operations in training, that will fall under the requirements of reporting. And if specifically for biological language models like protein or nucleotide ones, threshold is 10 to the 23rd operations. So that's kind of funny. And there's been a lot of discussion in the community, like how did you guys make up this number? Is it meaningful in any way? Is this the right metric on which to constrain things or have those thresholds? And the main difficulty is that policymakers are, in some sense, flying blind a little bit because compute is controllable and you can impose regulations on it, but it's capabilities that you actually care about, right? Those are the ones that are of potential concern. And so how does one connect the two? Right? You can't really regulate capabilities themselves, right? I mean, the testing for that would be unclear. And really, you want to be upstream of that. Right? And so what one would really want is an engineering theory that relates these resources like compute and data and energy, perhaps, to the capabilities that they have or lead to. Right? And that would allow kind of a solid footing for such regulatory policy. Right? And so that's an interesting engineering theory question. So what is the relationship between resources and capabilities? And it's been an open scientific question. Let me just briefly describe some attempts at thinking about it. Right, so here at Princeton, Aurora and Boyle, they proposed this theory for the emergence of complex skills in language models. And so what they did was they kind of abstracted away some of the details of how language modeling works. And they said that there's some text pieces, these square boxes, that have certain skills in them, essentially. So you can learn certain skills, and then the skill learning are the blue circles. And so, so what you see is that there's kind of this process by which you have this abstract learning happening. And if you analyze this asymptotically, then there's this kind of emergence flow. Okay? So it provides at least a little bit of insight into the fact that with increasing number of text pieces, you get kind of some growing skills and more complicated skills emerge. Right? So that was roughly what Aurora and Boyle argued. And if you're an information or coding theorist like me, when you see a graph like this, your mind immediately goes to low density parity check codes. So those are a class of codes that also have a bipartite graph representation. So they have kind of constraints and variables. And so what we've done recently is ask, can you analyze this in a more fine manner, this kind of model? Right, so what we've done, and this should be up on archive in a few days. So we have the same basic model as Aurora and Boyle, but we have text pieces, we have these skills, and then they connect a little bit into higher level concepts. And as you increase the compute budget, you can grow the number of text pieces that you can train with and so on. And the key kind of advance in our work is that we're using a non-asymptotic analysis. So what we can do is actually measure size as it increases and see what happens. And what we see is kind of several phenomena that emerge. So first is that we can provably show that the so-called chinchilla scaling, this compute optimal size scaling, is actually optimal. So the model size and the data set size do need to increase linearly with one another to achieve optimal learning. Secondly, that the loss, the training loss does decrease in the way people have described with the model size. But I think so this is kind of neat that there's nothing better than you could have done than the chinchilla scaling. But then you also see these emergence phenomena. So as you increase the size of the model, you actually do see this huge step increase in the capability. Right. So now we have a way to connect resources like the model size, which is related also to the compute budget, the flops, to this capability. And further, one sees that there's these plateauing and multiple emergences that comes out of the theory. So this is something that's only starting to be seen, that as you increase size, there's some plateauing of capability. But there hasn't been kind of empirical demonstrations of like next plateaus, but that emerges from the random graph model of what we're describing. Okay, so this is kind of neat that this kind of information theoretic model of language models actually predicts all the known empirical phenomena, but also shows that they're optimal. Okay, so cool. So this was an example of where engineering theory might relate capabilities and resources for regulation. One can also use this basic idea for net assessment. So net assessment is this idea that's often used in the Department of Defense of comparing oneself against adversaries, trying to assess which capabilities each of the different competitors might have. And this is usually done through technology forecasting, technology assessment and forecasting. So you might count the number of missiles that one country has and compare it against the number of missiles you have, or something like that. But how do we do this for, just to describe it. So like, for example, if you were doing something with semiconductors, you would look at data on the best semiconductors and so on, and then you would project that out into the future. So you would typically take empirical results and forecast from those. The other approach that I want to argue for is that you can use fundamental limits. So again, taking communications as the example, you can think about these curves. Those are the best that anyone can do, no matter how clever they are, and use that as a benchmark rather than just comparison against others. So what I'm trying to argue is that engineering theory-based absolute scales might be especially relevant for net assessment in settings like emerging technologies. So net assessment for things like military capabilities is somewhat straightforward for the intelligence community. but it's tough for emerging technologies that have strong private aspects to them, because intelligence community can't collect on domestic motors. Right? So if we can shift from this relative scale of comparison to absolute scales, it allows deeper insight into the capabilities of competitors. If we and our competitors are nearly equal and very close to the fundamental limits, it's suggestive that there's nothing more that will happen. Right? On the other hand, if there's gaps with respect to the absolute levels, then it can be things that we can consider. Okay. The third example of how engineering theory might inform policymaking is for industrial policy. When we think about architectures that come out of engineering theory analysis, and can they support socio-technical architectures? So let me just briefly read from an interview that Kirk Campbell, who's currently the Deputy Secretary of State. When this interview happened, he was the coordinator for Asia at the National Security Council staff at the White House. What he said was, speaking essentially about semiconductor supply chains, that I think we're probably heading into a new period when a new set of calculus is important: resilience, durability, the opportunity to be able to count on more than one source of supply. All these steps build redundancy into the system. I think probably those steps are smart and they will continue. But it is a substantial reorientation of the system that had been about just in time, that had been about maximizing efficiency over resiliency. I think we're reorienting towards a system that's more predictable. Might be higher cost in certain areas, might be slightly slower, but we think will probably be more durable in the event of a crisis. Okay. So again, so how would one build a semiconductor system that tries to achieve this property? Not the most obvious thing to do, is it? If anyone has thoughts, I mean, I'm happy to hear. I mean, this is a pretty big problem. Okay. How does one make the semiconductor system resilient to things like earthquakes and military actions and so on? As we saw during COVID, even like pandemics have a strong impact on semiconductor supplies because it introduces uncertainties both on the demand side and the supply side. So one can actually dig into computer architecture. So what one can try to do is architect multiple paths in the semiconductor system itself. So typically what one does is one separates the design of computer chips from the design of their supply chains. One treats them very modularly, very separately. And this was okay, largely because the cost per transistor used to decrease with decreasing size. Now, starting at the 7 nanometer level, there is not a decrease in cost as you decrease the size. Okay? And this actually makes a lot of difference. So one can't separate the technology from the management or the technology from the policy as we had done before. And so what one should do or one needs to think about is integrate the chip architecture design with the socio-technical architecture design. The technical architecture and the socio-technical architecture should be thought of collectively. And perhaps also in the so-called strategic manner, like how Eisenhower used to describe it, addressing several questions simultaneously. And there is this body of work on resilience of supply chains, but it doesn't consider the product itself, right? The chips themselves. Right? And so what we argue is that one can have careful chip architecture designs that draw on the engineering theory of modularity and so on, that can enable multiple paths to satisfy a given chip design. And three basic classes emerge. So first is composition. So the demanded chip can be built using multiple, sometimes disjoint sets of components, so-called chiplets. And this enables chip demand to be satisfied even if some of the components are constrained. So you can compose in different ways the larger system that you're after from the pieces. Secondly is adaptation. So a chip that's produced to satisfy a given demand can be replaced with a different chip. So there's this direct substitutability. And third is this idea of dispersion, that a chip built using a particular technology can be sourced from numerous suppliers, right? So all of these create these alternative or multiple paths in the supply chain by actually controlling the architecture of the chip, by having it be composable, adaptable, and dispersed across different sources. So this is, again, kind of a compelling architectural idea that comes from engineering theory, but it has these downstream impact on things like supply chain. Okay, so let me just pause here for a second and briefly talk about policy levers themselves. And this is maybe a little bit weird for, at least it's weird for me to think about. So maybe it's obvious for everyone else, but yeah, so theory itself can actually change.
Can I interrupt?
Yeah, please.
You talked about chip design and restructuring the architecture itself.
Right.
What about the cost side of the picture? To the extent that the manufacturers capital intensive, and the incumbent firms that have deep pockets are able to get maybe a 10-year lead in terms of technology.
Yeah. So that's exactly where a governmental policy lever would help. It would help maybe the newcomers to overcome that initial capex hurdle, and then they could compete with the incumbents. So that's exactly where
it'd be government subsidies.
Yeah, so that would be one way one could use industrial policy to get towards a system that's like this. That's right. So, for example, the level of investment that the CHIPS Act makes would get you much of the way there to overcome that capex hurdle. So, I mean, that's yeah, I mean, that's the argument for the specific policy lever.
But it's not just the funding; it's also the skilled labor.
Yeah, so chiplets are actually so-called heterogeneous integration. So they do require a little bit of a different skill set than monolithic chip design, but it's not so different. So my understanding, again, I'm not a computer engineer, but my understanding is that one can kind of repurpose existing talent from monolithic chips to chiplets and heterogeneous integration. But I mean, generally, one would need to grow the way. Anything else? Anyone else to talk about? Okay, so let me dive a little bit into theory itself as a policy lever. Right. As I was saying, it feels a little weird to me, but it's actually kind of compelling. Usually you think of theory as kind of a camera rather than an engine for changing the world. Right? So physical theories are often thought of as describing the physical world. Engineering theories are these theories of what can be and what cannot be, and so on. But there was this really nice book by Donald Mackenzie. It's called An Engine, Not a Camera. And his work he's a sociologist of finance, among other things. And so he was describing how financial models actually shape markets themselves. And then the term used for this was Barnesian performativity. So I'm just rephrasing it a little bit in terms of engineering theory, but it's the practical use of an aspect of engineering theory that makes the engineering designs or processes more like their depiction by engineering theory. Right, so the theory pushes the phenomena itself to be more as if it was described by the theory. He goes through this quite extensively with respect to finance. So in finance, what they saw was in derivatives markets and so on, that option pricing moved from a practitioner's rule of thumb to the more ethereal mathematics of stochastic differential equations of market. In Chicago, that mathematics was being performed in flesh and blood. The shouting, gesticulating, sweating, jostling bodies in Chicago's pits were actually enacting theorems. Okay, so yeah, very much, yeah, so the Black-Scholes formula for those who are familiar and others, right? So the fact that there was this theory kind of influenced trading strategies and it made them more like the theory, right? And so theories themselves can shape the world in their image in a sense. So I think the kind of the best example of this in in engineering theory is Shannon's universal interface of bits, and the rise of the digital age. So what Shannon showed was that there's a separation between data compression and error correction, and there's no loss in doing that. So you can have these bits right here, and you can measure information, you can characterize phenomena in terms of bits and so on. And that really shaped the world to be very digital, right? So without the information theory, there wouldn't have been this notion of bits, perhaps. So it kind of changed the world. So one can ask the same question now for other aspects of system design. So if you take this statement, joint statement on 6G that I helped draft, one of the points that's mentioned there is we want to support open, interoperable, resilient systems. Right, so modularity is kind of argued for in the joint statement, but is that a good idea or not? Right, as the United States, the standards policy is to support the technically best outcomes that ensures a globally fair playing field. Right, so one can ask in 5G and 6G wireless, is this idea of open architecture, is the so-called open RAN a good idea or not? And just to give a little bit of detail, so the way wireless systems work is that there's a radio unit at the base station. There's a device here. It goes back into the core of the network, and so on. And what Open RAN proponents want is the interfaces between these different components to be standardized and modular, so that different companies can be mixed and matched. Right? And so it raises the natural question: is there any loss in performance by having a modular design rather than a monolithic system? Because we do want standards that reflect the best technical solution. And Pramod is smiling, maybe he already knows the answer. I think it's still a fairly open question. Is there any loss in performance? Is there a separation theorem that having separated pieces is actually just as good as having a monolithic system? Right? If it turned out that there's no loss or very little loss from modularity, then it would support the argument from a technical perspective, and then that would go back into the socio-technical. Okay, so in this sense, the engineering theory could be performative. Okay, and then the final thing I wanted to briefly talk about was computational positivism. There was a historian of science named Joseph Needham who asked this question. So from like about 500 to 1500, China and India were kind of the world leaders in a variety of domains, including economic and technological strength. After the Industrial Revolution, Europe really took the lead. And you wanted to ask, why did Newton, arise in England, not in China or in India? And the basic argument so I mean, that was Needham's question. There was a recent historian of science from India named Radhan Narasimhan, who argued that the reason for this is because abstraction and theory building was more of a thing in Europe. In fact, people in India, for example, the Indic tradition is very skeptical of axiomatic approaches and lack of context. So because the theories of gravity, for example, and others were abstract, and they could be moved from one domain to the other, from apples to planets to anything else. And because of that, it was easier to transfer knowledge from one domain to the other. As compared to computational positivist views, which you compute the position of the stars specifically for the stars, you compute the apples for apples, etc. And there's no strong transfer of knowledge from one to the other. And so the argument is that here we want to develop kind of general purpose technologies that have theoretical foundations such that they can be transferred from one domain to the other, which is contrary to a lot of AI approaches, which are fully data-driven and fully computational positivists. And so one can again draw on information theory ideas, like Shannon kind of predicted. And so we've developed, in the interest of time, I won't go through the details, but we've developed this technique called information lattice learning, which goes back to Shannon's lattice theory of information. And it allows you to kind of learn concepts at an abstract level. So you can learn concepts in domains like shapes, So like colors and convexity and so on. Or in music, like things like sampling or what pitches are and rhythms and so on, as kind of abstract knowledge. And then you can use that abstract knowledge for learning things. So you can learn the laws of music theory from just a few hundred chorales by Bach, or the laws of neurogenesis from single cell RNA sequencing data, or the laws of ionic compound formation from chemistry. All using the same idea, which is fully human interpretable. Okay. One can learn to do things like image classification using only like 4 examples of each digit rather than hundreds like is needed for other techniques. Or kind of characterization of hand-drawn shapes. Or do optimal compression, achieving the information theoretic limits. Or do creativity. So one can develop songs that that mix the harmony and melody from Happy Birthday with the rhythm of Mozart to get something like this. So, so it's a fairly general purpose technology that is fully interpretable. So it's white box. It's easy to transfer from one domain to the other. Supports a bunch of different operations. It's computationally light. Uses very little data. Right? And so the point is that moving away from purely computational and data-driven approaches, these kinds of white box AI might facilitate diffusion of technology to numerous industrial and societal sectors. So, so with that, it's kind of was trying to make the argument that socio-technical policymaking can't understand the social without the technical, nor the technical without the social. And in particular, engineering systems theories provide a lens to understand the technical that's distinct from looking at specific technological artifacts or forecasting from specific artifacts. That this kind of approach to engineering theory might be insightful. And I think this lens, I kind of went through some examples in regulatory policy and industrial policy and so on. Might be applicable for other policy questions too, like R&D strategy and others. Just to give an example, like in quantum computing, is it better to invest more research efforts to make the qubits less noisy, or to develop algorithms and codes that work with noisier qubits, right? Which will give the more bang for the buck, essentially. Right? So, so broadly speaking, tried to argue is that this is kind of maybe a useful way to think about technology policy making, especially when there's so much uncertainty in the specifics of the physical artifacts. Let's think about what's possible and what's impossible, and use that as part of policy making. Thanks. Let me stop there.
Thank you. Thank you, Love. Any questions for our speaker? Yes.
I have a question on this new paper coming out on the limits of emergent states. So you talked about these various plateaus, right, that emerge in the model. So what determines the number of those plateaus, and how are they related to resources or the model size?
Yeah, those are determined by the complexity of the skill compositions that are needed. So the more diverse and complicated the concepts are, the more plateaus are needed. Yeah.
I had a quick question. In what sense was that, if you go back just a slide,
Yeah.
you mentioned something about IP liability. Actually, let's take a look at it. So yeah,
That's a
so
little.
maybe we can chat about this, but
Sure.
I just want to keep the time
Yeah, yeah.
correct. Any questions for our speaker? Final thoughts? Not, there is.
You mentioned this idea of like chip fabrication and sort of how we need to adapt supply chains around this. And when it came, one of the ideas that just like popped in my head when you asked that question was how like computer architecture structure inherently lends to many of these ideas around modularity in and of itself. The way that we design computer architecture systems are like that. Is there any examples of our ability to take these like technical solutions we've developed, which in many ways are abstracted block diagrams, and apply them to completely unrelated fields of policy, maybe like computer architecture, the ideas we can take from computer architecture, applying to social good policy around homelessness or things like that.
Probably, it's beyond my skills.
Okay.
So, yeah, I mean, I think, I'm sure some of these broad ideas are useful across domains, but I think it does require some depth of knowledge of the domain you're transferring to.
Okay.
Brilliant. Let's thank him and then we can
Yeah.
continue with the questions.